Generating a precise, explorable 3D environment from a single two-dimensional photograph is one of the most complex computing problems in modern AI. This capability enables rapid asset creation, allowing developers to populate VR spaces, build video game environments, and construct spatial simulations for robotics. Perspective shifts, straight walls curve, geometry becomes liquid, and sharp textures dissolve into a severe blur. This happens because foundation video diffusion models are highly optimized for painting 2D textures and predicting flat, frame-to-frame motion. They lack a rigid mathematical understanding of 3D coordinates. This 2D first approach makes geometric drift a mathematical certainty. Without explicit scaffolding, the model has no way to anchor its predictions to a fixed 3D space. This is why the GeoWorld pipeline provides external architectural constraints. The common solution to this distortion involves feeding the video model a single frame depth map or a spatial prior to guide the generation. This is like trying to draft the entire architectural blueprint of a house by looking exclusively through the front door's keyhole. When you rely on a single frame of geometric data, that data decays rapidly. As the camera trajectory moves away from the starting position, the mathematical certainty of the scene starts to fragment. These single-frame conditions represent incomplete 3D information, causing the model to guess, leading to geometric drift. GeoWorld inverts this. Instead of extrapolating from one image, it generates a video sequence first, extracting rigid geometry for the entire sequence all at once. Solving geometric drift requires abandoning the single-frame bottleneck. True spatial consistency only emerges from a multi-frame, sequence-first extraction methodology. To understand how GeoWorld achieves this, we have to look at the first module in its architecture, the geometrical condition generation procedure. Before casting a precise bronze statue, an artist has to pack together a rough clay mold to establish the general shape. The system needs to create a structural rough draft before it can refine the details. This begins in the rendering phase. The pipeline takes the single input photograph and physically projects it along a specified 3D camera trajectory. By moving a virtual camera along a defined curve, the system is stamping out multiple new viewpoints, creating a sequence of fragmented 2D image planes. The source of this projection data actually differs depending on whether the model is in training or inference. During training, the system extracts precise depth maps from fully reconstructed 3D Gaussian splatting datasets. But during inference, it relies on point cloud estimations from models like Master to estimate the depth. This deliberate separation keeps the model stable during training, while still ensuring it can construct the foundational, multi-view fragments needed to build a brand new 3D space. The immediate result of the rendering phase is a sequence of fragmented views. The timeline is filled with blind spots where the initial projection couldn't reach. To solve this, the pipeline enters the completion phase. A specifically fine-tuned video diffusion model takes over to process the fragmented renders. Its singular job is to fill in the missing pixels and seamlessly stitch together the blind spots between the physical projections. The output here is a coarse, content-complete video. It serves as a proxy sequence. It doesn't need to be perfectly photorealistic. It just needs to be structurally cohesive across time. At this specific step in the architecture, the diffusion model is operating with a handicap. It is only being guided by single-frame geometry features embedded via standard cross-attention, but that is enough to produce the rough draft. This proxy video provides the necessary multi-frame data, converting a single flat image into a timeline ready for deep geometric extraction. With a cohesive proxy sequence built, we reach the core innovation of the paper, extracting the actual mathematical scaffolding from the newly generated video. The pipeline feeds the proxy video into a large-scale geometry model, like VGGT or Fast3R. This acts as the architectural engine of the system. It analyzes the coarse video and outputs dense, full-frame 3D features. This includes camera extrinsics, tracking position, intrinsics, mapping the lens, and rich point clouds for every single frame in the sequence. But diffusion models process 2D noise, not rigid 3D arrays. To bridge this gap, the pipeline uses a geometry adaptation module, or GAM. The GAM operates as a translator. It compresses and interpolates the rigid 3D point cloud data into a series of flat, sequential data tokens. A multi-layer perceptron adapter takes these newly flattened tokens and injects them directly into the diffusion model's UNet architecture. The GAM effectively translates a complex 3D architectural blueprint into a language that a 2D painting algorithm can execute. Even with the best blueprint, there is a risk. What happens if the diffusion model ignores the cross-attention geometry tokens and hallucinates a new structure instead? To prevent this, the researchers implemented a strict mathematical enforcement mechanism, the geometry alignment loss, or GAL. Think of the GAL as a building inspector. Instead of waiting to inspect the finished skyscraper, it checks the physical scaffolding at every single floor during construction to ensure the builders are following the blueprints. This chart plots geometric divergence during generation. The red line represents the base model without enforcement, resulting in unstable geometry. The blue line shows the system with GAL active, staying flat at 0. The GAL accomplishes this by penalizing any geometric divergence between the model's predicted multi-view frames and the actual ground truth video during training. The paper's ablation studies confirm this dynamic. Without the loss function, the model drifts and reverts to distorted, melted outputs. With it, absolute multi-view consistency is maintained. The geometry alignment loss is the non-negotiable anchor of GeoWorld. It is the specific mathematical mechanism that forces a probabilistic generative model to produce physically accurate 3D scenes. With the geometry strictly enforced, the pipeline takes the mathematically constrained predicted views and pushes them into the final 3D Gaussian splatting reconstruction. The resulting video demonstrates high spatial stability. Surfaces remain rigid and architecture stays fixed even as the camera sweep completes. By separating the underlying geometry from the surface texture, GeoWorld maintains absolute global semantic consistency. It outperforms view-by-view in-painting models, which often lose track of where objects should exist in a unified space. However, the architecture has a specific vulnerability. The entire structural integrity of the pipeline hinges squarely on the success of the initial completion phase. It is a case of garbage in, garbage out. If the fine-tuned video model fails to generate a cohesive proxy video in step 1, the geometry model will extract useless scaffolding, causing the final output to collapse. GeoWorld significantly improves the generation of static architectural environments, but handling highly dynamic scenes filled with non-rigid motion, like flowing water or moving crowds, remains a future challenge for the geometry adaptation module. When we review the research, GeoWorld introduces 3 distinct shifts in how we approach 3D generation. This graphic summarizes those shifts. Let's break them down. First, single-frame spatial priors are mathematically insufficient for consistent 3D generation. Relying on them leads to inevitable geometric drift. Second, stable generation requires full-frame geometry. You have to extract the 3D data from a coarse proxy video sequence rather than a single starting image. And third, you cannot trust the diffusion model to maintain structure on its own. You must use mathematical alignment loss to physically constrain the network. That's it for this breakdown. Thank you for watching. If you want to keep exploring the underlying math and architecture of the latest AI systems, hit subscribe. We'll see you in the next one.